Okay, so in this next set of videos, we're going to learn how to actually solve some systems of differential equations. And in particular, we're going to focus on the homogeneous case, first of all, and the constant coefficient case. So we're going to think about linear systems of differential equations, which are constant coefficient and homogeneous. The method that we're going to use to do this is called the eigenvector method. And eigenvectors and eigenvalues, these are concepts that we borrow from linear algebra, but they are very, very important in and of themselves. They are important for your life. Whenever I say that, it's because I had a math teacher when I was an undergrad. I asked, why do I have to learn about tensor products? Is this really is this important just for the representation theory that I was learning at the time? And he said, no, 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 no. This is important for your life. And that just really hit me right in the heart, and I took it really, really seriously. I'm telling you, you got to take this stuff very, very seriously. It is important for your life. Okay, it's going to come up not just in this class, but in many, many different contexts, and it's always incredibly useful. This formalism that we're going to learn from linear algebra. But let's first see why this concept comes up, or how it comes up in the context of differential equations. So we're going to be learning about eigenvectors and eigenvalues. Here's the idea. We're going to consider equations like x prime equals p times x. And don't forget, x here, or sorry, P here is going to be an n by n matrix with constant entries. X, though, is going to be, you should think of it as an n by 1 column vector. It's an n by 1 vector with non-constant entries, or not necessarily constant. I'll just say non-constant entries. Yeah, it's a vector of functions, x1, x2, x3. Those are all functions of t. All right, and they're arranged and organized in this vector here. And when we write this equation here, we literally mean that we're going to take this matrix, n by n matrix here, and we're going to multiply it by this n by 1 matrix there. Okay, and the result, if you understand matrix multiplication, is n by 1 again, and it, to satisfy this equation, means that p times x is the derivative of x, which is simply the entry by entry derivative. Okay? All right. So that's the setup. Now, what we're going to do is make a guess. In German, sometimes they call this guess an Ansatz. The ansatz that we're going to make, the guess at the solution, is the following. We're going to guess that x looks like v times e to the lambda t. Let me, I know letters, there's a lot of them here. V is going to be a n by 1 vector, and this will have constant entries. And lambda is just, it's going to be a real or complex number. It's just going to be a number. I'll just say it's a number, a constant. Okay, and eventually we're going to learn that lambda will be what we call an eigenvalue of, turns out, p. Why? So let's think. This is our guess for a solution. This is our guess for a solution to this equation here. So now what we're going to ask ourselves is what needs to be true in order for this guess to really be a solution? Well, we can compute x prime, no problem. X prime is, so v is a constant, so, you know, taking the v, it's like, think of the constant multiple rule. We're not going to mess with that. But the derivative of e to the lambda t by the chain rule is lambda times e to the lambda t. Right? So I just put a lambda out front. That lambda is a constant. Okay, don't get it twisted. So then plugging in this information here into this system gives us the equation. Let's see. So on the left-hand side, we get lambda v e to the lambda t. That's x prime after all. And on the right-hand side, we get the equation p times v e to the lambda t. Okay? Now we know that the exponential of anything is always non-zero. If anything is positive, then in fact it's positive. And so we can divide both sides by e to the lambda t. And where we arrive is lambda v equals pv. This is very important because this is what's called the eigenvector equation. This is the equation that tends to crop up again and again in many, many different contexts, okay? When you see an equation like this, what that's telling you is that you're in the world of eigenvectors and eigenvalues, okay? Let's interpret what this equation is saying. Very important, okay? Don't sleep on this. So P, don't forget, is an n by n matrix. And we're going to multiply v by p. Now, in general, when you have a vector v and you hit it by a matrix p, anything can happen. That vector could rotate, it could stretch, it could flip around, it could do so many different things. So like in general, you're going to have pv being just almost like a random vector out there in the plane. But what this equation is saying, what the eigenvector equation is saying, is that if v satisfies this equation for some lambda, delete, then in fact what happens, so if this is our v, then when we hit by p, all that happens is we stretch, we multiply v by this number lambda. So you can think of it like all that p does to v is stretch this vector by some amount. Like maybe this is lambda v. Sorry, let me do this a little bit differently. Lambda v, which is our pv, right? It just stretches v. So it doesn't point in, pv doesn't point in a different direction. It could be the case that it like flips it around a little bit, right? This could be lambda v, I don't know. It depends on lambda, right? But the point is that whatever p does, it's not that complicated. P doesn't do anything all that complicated to v. It just simply scalar multiplies by v. Okay? That's what the eigenvector, that's how you interpret the eigenvector equation. So with that in mind, let me make the following definition. And now we're really going to venture into the world of linear algebra. Definition. An eigenvector, I'm defining this formally, V of a matrix, square matrix P with eigenvalue lambda. So really, I'm defining the notion of eigenvector and eigenvalue all at once, okay? So an eigenvector is a non-zero vector. It has to be non-zero for important reasons. Is a non-zero vector v such that, which satisfies the eigenvector equation. Lambda v is equal to p times v. Excellent. Okay. And again, the interpretation is that what p does to v is simply stretch the vector. It doesn't do any fancy rotation. It doesn't move it out of off the sort of line that's determined by v. Hopefully that makes sense. Okay, so the question which is going to preoccupy us for the next 40 minutes is, how do we compute eigenvectors? So to answer this question, actually, let me make this black to make it clear. This is a new section, style black. To answer this question, I'm going to need to do some linear algebra. And in order to do this linear algebra, to do this in concise form, I'm going to have to shove some facts down your throat. Okay? So, first fact. So, facts from linear algebra. That I'm just going to shove down your throat. And I don't expect you to understand why these things are true, but I do want to motivate the eventual method for finding eigenvectors by showing you and telling you what facts from linear algebra we kind of need in order to make this work. So if you have a square matrix, and you think about the equation ax equals 0. So x here is, again, it's a so A is a square matrix. Maybe it's got n rows and n columns. Okay, n rows, n columns, and then x is going to be an n by 1 column vector. Okay, and you're going to do A times x, and what you want to see when you do A times x is the 0 vector. Okay, you want to find x, which makes that happen. So if A is a square matrix and you want to solve ax equals 0, one obvious solution is x equal to 0. But let's say that you want a solution which isn't stupid like that. That's sometimes called the trivial solution, right? Let's say that you want a solution which is not just x equal to 0, and that can happen. This equation has, and this is the fact, this equation has non-zero solutions if and only if, and this is the crucial condition, the determinant of A is equal to 0. If and only if the determinant of that square matrix is 0. Okay? So it goes both ways. So if you know that the determinant of a square matrix is 0, then if you go to solve ax equal to 0, you're going to find non-zero solutions. Okay? And if you can find non-zero solutions to ax equal to 0, then you know it must be the case that the determinant of A is 0. Okay? There's something degenerate about matrices for which ax equals 0 has non-trivial solutions, non-zero solutions. Okay? They are a rare breed, but they're a rare breed which you can track using precisely the determinant. Okay, so the determinant is quite an important quantity here. All right, actually, you know what? I said I want facts from linear algebra, but I think this is everything that I need. So maybe let me just demonstrate this fact with an example, and then we can talk about then we can talk about computing eigenvectors. I believe. I hope. Let's just see. Okay, so example. Let me show you what I mean here. Let's take a let's write down a matrix, maybe a 2 by 2 matrix. Let's call this matrix A, and I'm going to make a matrix which has determinant 0. How about 2, 1, negative 4, 2, negative 2? Okay, so notice that the determinant of A is equal to negative 4 minus negative 4, right? I did product of the product of the diagonals, which is negative 4, minus the product of the off diagonals, which is minus negative 4. So I get negative 4 minus, that's 0. So if the statement that I've given you here is true, this statement here, very important fact from linear algebra that I'm shoving down your throat, foie gras style, yes? If that's true, then I should be able to find a non-zero solution to ax equal to 0 for this A. Can I? So let's solve ax equal to 0. Okay, so how? So this is where we get into that idea of solving linear systems, right? Where we talked about row reduction and all of that kind of stuff. If I write down the matrix, write down the what's called the augmented matrix. Augmented matrix. Which is going to have A in the first two columns and then the zero vector in the third column. Zero vector. So this is going to be the matrix 2, 1, 0, negative 4, negative 2, 0. What I'm going to do now is row reduction. Okay. So what am I going to do? I'm going to row reduce this. So I'm going to add negative 2 row 1 to row 2. And when I do this, what happens is I obtain negative 2, 1, 0, and then 0, 0, 0. That's the point. You can check that yourself. Okay. So what is this matrix saying? So remember, when you apply what are called elementary row operations to a matrix, you do not change the solution set of the associated linear system. So I can go from this matrix that I did after doing one row operation, and I can reinterpret it as a linear system. If I call the variables for x, x1 and x2, so suppose that x is given, I just label the components, x1 and x2, the entries, x1 and x2. Then what this system here is, what this matrix, this augmented matrix is representing is the linear system 2x1 plus 1x2, so just x2, equals 0. And notice that the second equation, which has a row of zeros, okay, is it's quite trivial. It doesn't give you any information, because what is it saying? It's saying that 0x1 plus 0x2 is 0. And like, no duh, right? That's true for literally every single x1 and x2. Do you understand what I'm saying? So that second equation doesn't give you any constraints on x1 and x2. So you can basically ignore that second equation. It's really the first equation which is doing all the work. And what is the first equation saying? So this first equation here tells us that 2x1 is equal to negative x2. So what I can do, or maybe another way of saying it that's better, is that negative 2x1 is equal to x2. So what this is telling me is that I have that x is going to be of the form, all right, x1 for the first entry, and for the second entry, negative 2x1. In other words, x2, because it is equal to negative 2x1, I can just replace the x2 here by negative 2x1. Are you with me? And what this means is that you can let x1 be whatever it wants to be, okay? Where x1 is an arbitrary element of the real numbers, let's say, okay? And what you're going to obtain with x is a solution to ax equal to 0. So for instance, if x1 is equal to 3, and we sometimes call x1 a free variable here, x1 can be whatever it wants to be, but if we make x1 be equal to 3, then we get the equation, or we get the vector x1 equals 3, negative 6. You see how I did that? I just plugged in 3 into this x here, right? Now check. We can check that if we compute ax in this case, what we get is 2, 1, negative 4, negative 2 times 3, negative 6, yes? And now we just do the arithmetic. 2 times 3 is 6, minus 6, oh my god, that's 0. Good sign. Negative 4 times 3 is negative 12. Negative 2 times negative 6 is positive 12, and that's 0. Oh my god, we got 0. We got the 0 vector. Okay. So indeed, what this confirms is that this non-zero vector, it's manifestly non-zero, I don't see zeros there, is a non-zero solution to ax equal to 0. And the way we can detect that is the fact that the determinant of this matrix is 0. Okay? This is the point that I want to make. All right. I'm going to end this video here. Make sure you understand this idea that, again, the most important thing that I said today, besides the eigenvector equation, that's the most important thing. But the second most important thing that I said today is that if the determinant of A being 0 is equivalent to the matrix A, a square matrix A, having non-zero solutions to ax equal to 0. We're going to use that to the hilt in the next video to compute eigenvectors and eigenvalues. Okay, see you in the next one.